Hello everyone, welcome to the second part of our 29th lecture for MAT353. So we are now moving into, we're actually dropping back to chapter 13. We are going to spend just the remainder of today's lecture on chapter 13. We're going to pick up what we need quickly, and then with our next lecture we'll be moving into chapter 16. I don't like the order that Stuart puts this material in, so I'm chopping it up and rearranging it. I feel like this is a more natural progression. So, chapter 13 primarily concerns itself with vector functions, also known as vector-valued functions. So we'll begin here with a definition. We'll look at some intuition behind this definition, and we will also take a look at some examples. So r hat of t, here my function is r, I'm giving it a hat to indicate that the output is going to be a vector, and it is a function of parameter t. It is a vector function if it is a function from the reals into r to the n, where n is either going to be 2 or 3 for our purposes. So it is a vector-valued function of one real variable. If it is mapping into R2, then it will look like this, where r hat is given as a vector, a two-dimensional vector. The x component is itself a function, a real-valued function of one real variable, so little f takes a real number in and spits out another real number, and likewise for little g. So r hat, which is a vector-valued function, is composed of two normal or usual scalar-valued functions stuck together inside a vector notation. If instead you want to talk about vector-valued functions mapping r into R3, then you've just got three scalar-valued functions glued together with the vector notation. These scalar-valued functions that a vector-valued function is built out of are called component functions. They are also sometimes called parametric equations in a context where they're written in this way. So if you tell me that your x component is little f, your y is little g of t, and your z is little h of t, as in this expression, then we might refer to these as the parametric equations. I tend not to favor the parametric equation formulation, but it shows up in a lot of the WebAssign problems. So you'll see some on the homework. You'll be asked for parametric equations, and this is what they're looking for. X equal to a function of t, y equal to a function of t, or whatever your parameter variable is, and z equal to that function of that variable. And note that this expression here with f, g, and h, I could equally well write that as f times little I hat, g times little j hat, and h times little k hat, if you prefer the basis vector notation that the physicists often favor. So, intuitively, how does this type of function fit in with the other kinds of functions that we have seen, and even some functions that we are yet to see? Our study of mathematics, of functions in mathematics, generally begins with real-valued functions of one real variable. So these are the functions we've been studying since probably middle school or so, things like f of x equal to x squared. In this course, we've begun to consider in a serious way real-valued functions of multiple real variables. So mapping Rn into R. And these are things like this polynomial, which we could look for critical values of if we chose, and we can take partials, we can integrate such things. So we've begun to study in chapters, I guess it was 14 and 15, partial derivatives and multiple integrals. We studied these functions extensively. This is now a function mapping R into Rn. So its input is one-dimensional and its output is multi-dimensional, either two- or three-dimensional for the purposes of this course. Again, these are functions which take a single real number as input and they return vectors as their output. That's the fundamentals of it as a function. I always think of functions as black boxes. It's a little machine. You feed it some input, it spits out some output. Vector functions spit out vectors, and in fact get fed real numbers in order to spit out vectors. The last type of the last broad category of functions that we'll consider in this class will begin with the next lecture, lecture 16, and these are what are called vector fields. These map Rn into Rn. So mapping the plane to the plane, mapping 3 space to 3 space, and so forth. So hopefully that helps to put this in context. Again, we introduced this input-output notation in this course simply to keep track of all of the different types of functions that are floating around at this point. What is the dimensionality of the input space? What is the dimensionality of the output space? Also known as domain and range. So we've actually seen one vector-valued function already. Back when we were in chapter 12, we considered parametric equations for a line, or a parametric representation for a straight line in the plane. And when we did that, we had some point that we wanted to lie on the line. We had the vector version of that point. We had a vector that indicated the direction that the line should move in. And we said that we can take this vector version of the point and we can add all scalar multiples of our direction vector. So I've got my vector version of the point plus an arbitrary scalar multiple of the vector v. And I can simplify that expression to this type of a representation, and this was good for t anywhere between negative infinity and infinity. I should not be allowing equality here. Let that be negative infinity strictly less than t, strictly less than infinity. So this is a vector valued function. There's 2 points to consider here in the overall. First is that this r hat of t that we've defined, it does take real numbers as input, and it outputs vectors. And I'll also say that the curve that we're considering, here it's a straight line, so it's not a very curvy curve, but the curve, quote unquote, that we're considering is the collection of all possible outputs associated with this function. So you can imagine your t starting way back somewhere for very large negative values, and there's a point on this line that's associated with it. If I plug in t equal to negative 10 to the 10 or something, that's going to give me a vector here. That vector I could draw with its tail at the origin, and its head would just touch a point way back on this line. As I allow t to increase, I could consider a bead on a string which is going to slide along this line as t increases. Right here would be t equal to 0, here's t equal to 1, and as t continues to increase, my bead on my string would continue to trace out this line, would continue along the line that is the string in that analogy. So every value of t represents a point on this curve, and as we let t increase, that point traces its way down the curve in question, here a straight line. And all of the outputs taken together, written as vectors with their tail at the origin, they give you the whole of the curve, here this straight line. So this was something we talked about back in chapter 12. It was in fact an example of a vector valued function, though we did not yet have that term defined. This is our first example that we've already seen of such functions. We can do similar things with more interesting curves, with things that aren't straight lines necessarily. So for instance, if I let r hat of t be 2 cosine t, 2 sine t, and I'm going to let t here go from 0 to 2 pi, this is actually a parametric representation of the circle of radius 2 centered at the origin. And in fact, it is a parameterization of this circle that is going to get traced out counterclockwise. So you can follow along with this. If you plug in t equal to 0, I actually plug it in to these equations. Cosine of 0 is 1, sine of 0 is 0, so I get vector 2, 0. So r hat of 0 is going to be the vector 2, 0. If I draw that with its tail at the origin, its head just touches this easternmost point of the circle. As I let t increase, my bead on a string starts to rotate around. So here's its value when t is pi over 2. It continues to rotate. Here's its value when t is pi. T equal to pi, 3 pi over 2. And when t is 2 pi, we've returned to this easternmost position, point 2, 0 in the xy plane. So this is a parametric representation of this circle. If I let t go out to 4 pi, for instance, my bead would just trace the circle twice and come back to the same resting point. So this is a parametric representation of the circle of radius 2 centered at the origin. I can take a circle of arbitrary radius centered at the origin by replacing the 2 with an r naught. So I can form a parameterization of an arbitrary circle of radius 2 centered at the origin by letting r hat of t be r naught cosine t, r naught sine t, and allowing t to be from 0 to 2 pi. This is a parameterization of such a circle traced in the counterclockwise direction as we mentioned here, and in fact traced exactly once. There's only one point where our circle overlaps, and that's the beginning and the ending here. If you really wanted to be strict, you could knock one of these out, like make the 2 pi t strictly less than 2 pi instead of less than or equal to, and then there wouldn't be any points that double up, but it doesn't hurt anything. So it's worth noting here that for vector valued functions, it's not enough to just give the equations. You also have to give the interval where your variable t, your parameter t, or whatever symbol you use to designate the parameter, what are the values that are allowed for that variable? T is fairly typical. So like, what is the interval where t is allowed to live? I could give you a formula, for instance. There's two components to the definition of a parametric representation of a curve. You have to have the formula, the vector, the definition of the vector that is going to be the output for this function. But then you also have to have the bounds where your variable t lives. I have no idea what this one actually looks like. I'm just throwing some stuff together here. But this would be the formula. It's going to give me my vectors for any input. And then I have an interval which tells me what my allowable input are. And this collection of allowable input, it could look like a bunch of different stuff. So it could be the whole real line here, which is what my interval should have looked like when we discussed that parameterization of a line earlier. You don't generally allow the variables to be equal to infinity. Or I could take t going from 0 to 2 pi with both of those endpoints closed, so the 0 and the 2 pi are both included in the interval. I could take 0 less than or equal to t less than 1, so that 0 is included and 1 is not. I could take a half infinite interval, 0 less than or equal to t less than infinity, and so forth. So it's going to look something like that. Whenever you are, if I were to ask you for a parameterization of a curve of this type, you have to give me the vector definition, and you have to give me the limits or the interval, the limits on your parameter t, which is to say the interval where t lives. So here's another one. Let's let r hat of t be t cosine t sine t, where t is taken to be non-negative, so greater than or equal to 0. If we were just looking at the yz components here, if we ignore x for a moment and we just think about what this thing looks like in the yz plane, I see cosine t sine t, so that's actually a parameterization for the circle of radius 1 centered at the origin, the unit circle centered at the origin. So if we were just looking at the yz plane, we would see the unit circle centered at the origin, but then with t allowed to increase indefinitely, we would see that circle traced counterclockwise over and over and over again. So it's just going to keep circling endlessly. That's what it looks like in the yz plane, but our x variable is actually increasing at a linear pace here as t increases. So if you look straight down the x-axis and see the yz plane, you will see that circle occurring over and over again. But as you pull away from the x-axis and look at it from the side, you see that the point is actually moving down the x-axis in such a way that we're seeing a helix, a kind of regular cylindrical spiral occurring as we move down the x-axis here. So it's like a spring, it's like a slinky, if you're old enough to remember what slinkies look like. It looks like I was about to say a coiled up old phone cord, but those are also fairly obscure at this point. It looks like a helix. That's the mathematical name for it. So curves of this type, curves that live in 3 space, are known as space curves, and that is in contrast with the phrase plane curve, a curve that lives in the plane. All of these vector valued functions, their graphs, the picture you could draw that's associated with them, it's always going to look like a one-dimensional object in some sense, a curve of some kind that lives in some higher dimensional space. It could be 2 space, it could be 3 space. There's no problem with thinking about 4 space, though we won't consider those examples in this course. So there's another one, another parameterization, and one where we can sort of, by thinking about what's going on in one of the component planes, we can piece together what the actual space curve looks like. For some functions it's easier, backing up for a moment. For some functions, it can be a little bit more challenging. Not saying that you can't think about what this looks like. You could probably figure it out. I can see it now that I think about it a bit. But there are ways to try to visualize these things generally. So another example, we've talked about the parameterization of straight lines. We've talked about the parameterization of circles centered at the origin. We looked at a helix. Another common parameterization that you might be interested in is when you want to create a parameterization for the graph of a well-known function. So something like f of x equal to x squared, which we're going to look at as an example, f of x equal to sine x, f of x equal to e to the x. There are many famous functions that we're familiar with the graphs of, and we may want a parameterization of such a graph. We may want a vector-valued function whose outputs are going to be like a bead on that string that traces its way along that string, the string that is the graph that we know well. So let's take f of x equal to x squared and think about this. If I let r hat of t be t, so x is just t effectively. I'm making the x-axis into the t-axis in some sense. and then I let y be x squared, so t squared. So this is like taking x and then y equal to x squared is the idea. And I'm going to do that for all values of t. Again, I should not be allowing equality here. That's a typo. Imagine this: less than infinity, negative infinity, strictly less than t, strictly less than infinity. The curve delineated by this parameterization is the graph of x squared that we're used to. So for my, whenever t is large and negative, I've got a bead on the string that's way up here somewhere on the negative side, or on the left side of this picture and way up high. As t starts to increase, that bead swings around, passes through the origin at t equal to 0, and continues on up to the right as t goes to infinity. So the parameterization of this curve is given in this way. And again, the idea is just let t be the x-axis, and then y is already defined in terms of x. That becomes a definition for y in terms of t, just replacing x with t. So it works here for x squared. In general, you can do it for any function, any real valued function of one real variable. So if f maps r to r, then r hat of t given by t comma f of t, where this time I caught myself, and I'm trying to let t be strictly between negative infinity, negative infinity, and infinity. This combination of two lines, this specification of the vector together with the interval for the parameter, is a parameterization for the graph of f, whatever f may be. F could be sine of x, y equal to sine of x, or f of x equal to sine of x, and I would end up with a parameterization for the curve, and that would look like a bead on the string that is the graph of sine, and that bead would bounce up and down as it moved to the right as t increased. So that'll do that. We are going to, in the next part, in the final part of this lecture, we will be talking about calculus on vector-valued functions. Again, there is more that could be said here, but we're taking what we need from these sections so that we can move into talking about vector calculus proper. I thank you, folks. I will speak with you again shortly.